imagination or comparison to other industrial applications that these canisters should be pristine, polished, perhaps even futuristic in appearance. The reality is more grounded. Our dry storage canisters are robust. They're made with industrial grade special stainless steel containers. They're designed to function, not designed for aesthetics. So our goal today is to bridge the gap between perception and reality. We want to share the facts, answer your questions, and reaffirm our commitment to safe, transparent, and responsible stewardship of spent fuel. I'd like to move to the next slide, and next one. Thank you. As you mentioned, joining us virtually tonight is Dr. James Byrne of the University of Virginia. Dr. Burns is a materials specialist whose focus is understanding how different environments impact the mechanical properties of materials. His work cuts across infrastructure, aerospace, marine, oil and gas, medical, automotive, and of course, nuclear. Even if it's only a small portion of Dr. Burns' work, he's worked with NASA, with the US Navy, and the Air Force. In the private sector, Dr. Burns has worked with Grumman, with Rolls-Royce and others. He's also worked with the Department of Energy and has conducted award-winning work that has been recognized by NASA and the federal government. Dr. Burns will help us understand what it takes for chloride-induced stress corrosion cracking to initiate on a spent fuel canister. He has reviewed the 1,749 canister images and will share his takeaways. Welcome, Dr. Burns, and with that, I'll turn it back to you, Dan.
Thank you, Fred. Next slide, please. Next, we will have Manuel Camargo, and he'll discuss the efforts to move the spent fuel offsite. Manuel, the floor is yours.
Thank you, Dan. Good afternoon, everyone. Pleasure to be here. I would pick up on a theme that Fred mentioned, which is that the spent fuel was never intended to be at songs in perpetuity. The spent fuel that we currently have in dry storage, per federal law, was supposed to be starting to get picked up back in 1987, and so 27 years behind plan is the federal government. So at this point, the federal government is not in compliance with its own federal law. So instead, some years ago, nuclear plants, including songs, started to store the spent fuel on site. There are a variety of reasons why that is inappropriate. It's very expensive. First off, the utility ratepayers paid in advance for solutions, and there's $50 billion that sits in the nuclear waste fund today that's supposed to be used for the disposal of spent nuclear fuel. That failure in reimbursing utilities for on-site storage that was never in the plan, that costs another $2 million per day, and about $11 billion total, so significant waste. And just from sort of a fairness and generational equity standpoint, we shouldn't be passing this problem on to the next generation. So we are committed to safely storing the spent fuel on site, but we also are not satisfied with the status quo. So next slide. Oh, I already talked about this. If you can go to the next slide. Yeah, so SCE is not okay with the current situation. Of course, we're safely maintaining the spent nuclear fuel. The point here is that we are very active in trying to relocate the spent fuel off-site. If you go back to 2021, we released the strategic plan that looked at, that analyzed a variety of alternatives to be able to get the spent fuel relocated to to either an off-site storage facility or a permanent disposal facility. And one of the key things in that report that speaks to some of the behaviors that you'll see from us is that our advisors that helped develop the strategic plan stated in the plan that SCE really cannot go it alone, but we can help to catalyze action. And so we have worked very hard to try to catalyze action. One of the ways that we've done that is to form a coalition, an advocacy coalition, the Spent Fuel Solutions Coalition. Supervisor Desmond is one of the co-chairs, Supervisor Foley is the other co-chair, and so that organization, it's through that organization that we are trying to really move the needle. And tell you that it feels like we have a little bit of a window of opportunity here. This is the issue related to spent nuclear fuel does have bipartisan support. You don't see a lot of bipartisanship if you watch evening news, but this is an issue where I think you do see folks on both sides of the aisle considering new nuclear, and in some respects then looking to solve the back end of the fuel cycle if we're going to be serious about new nuclear. So the work of the coalition and the work that we at SCE do to try to advance this basically breaks down into three categories. One is to raise awareness for the issue. The disposition, offsite disposition of spent nuclear fuel really suffers from a lack of attention. Number two is supporting DOE's work. So the Department of Energy is in federal law, the agency at the federal level that is responsible for the offsite disposition of spent nuclear fuel. And they are working on at least part of the problem at present, storage. So we're supporting that. You've seen a lot of activity over the years where demonstration projects and such, so keep an eye on that. But that's sort of theme number two, is working with the DOE to help it be successful, because DOE is successful even with storage. Their success is our success. And then the last piece is most important, and that's legislative reform. So clearly, the Nuclear Waste Policy Act of 1982, amended most recently in 1987, is failed legislation. So there are some key ways that we would look to amend federal law in order to provide for a more integrated spent fuel program that is durable, can survive various changes in administrations, and would provide for near-term storage, off-site storage, and permanent disposal of spent nuclear fuel. So those are things we're looking for. There's a little bit more information in the appendix. And then, of course, on the Songs Community website, you can find the strategic plan and get a lot more depth. We also have spentfuelsolutionsnow.com, the website for the coalition. I would just ask anybody who is concerned about the spent nuclear fuel, if you want to try to make a difference, please do consider joining Spent Fuel Solutions. By going to that website, spentfuelsolutionsnow.com, you can very quickly sign up and lend your voice to our efforts.
Thank you, Manuel. And we're fortunate to have San Diego County Supervisor Jim Desmond here. And Jim, I think all of us want to thank you, and you and Katrina Foley for co-chairing this effort. I know you went back to Washington, D.C. A few months back. I wondered if you could fill us in a little bit on how things are going.
Well, appreciate it, Dan, and the Spent Nuclear Fuel Coalition. We have been meeting, and actually I'm going back to Washington D.C. this month because we weren't able to fix it the last time we went there. But you know, it's as Manuel had mentioned, the coalition. You know, we're primarily there to raise awareness and to get other cities and the counties to collaborate in this effort. We've hired Southwest Strategies as a PR firm to help us get the word out as well. And, you know, as was mentioned, not only the awareness factor, but to support legislative reform. And one of those reform items we've been looking for is to have a standalone agency instead of the Department of Energy or some other department, have a standalone agency that is funded, which has no political strings attached to deal with the issue of spent nuclear fuel. So that's been one of our efforts, and we know there's still work to do, but then, you know, the more people in offices and doors we can knock on in Washington, D.C., hopefully the quicker we can get to removing the spent nuclear fuel. Thanks.
Great. Thank you very much, Jim. I just want to turn to my fellow CAP members to see if there are any other questions from anyone. Oh, Martha, hello. Good to see you.
Oh, sorry, I snuck in.
That's okay. Good to see you. With seeing none, let's go and move on to the next slide. Next, we're going to have Jerry Stevenson, who will discuss the song Spent Fuel and how we got there. Jerry.
Thank you very much, Dan. So it's going to be a lot of technical stuff, especially with when we get to Dr. Burns. And some of the stuff you may have heard before, but a lot of new stuff mixed in. It's all part of the story, how we got here. If you hear something you've heard before, don't think I've heard this before and tune out. There's a lot of important material here that I think you'll be interested in. Next slide. Okay, so it all starts with, uranium pellets, uranium dioxide pellets. So they're a ceramic material that's like glass, only harder, stronger, and beefier and tougher. Doesn't melt until 5,000 degrees F. That's much hotter than the temperature it takes to melt steel. So you couldn't make a steel pot to melt ceramic pellets, right? Our fuel's been cooled for 13 years, okay? So we shut down in 2012, and so our fuel's been sitting there cooling. And as a result, a fuel assembly, you see there's a fuel assembly there in the bottom picture. One fuel assembly has about the same amount of heat as a hairdryer. So it doesn't take much to cool these assemblies, okay? And of course, if you did have they go into a canister, and I'll talk more about canisters later. Next slide. Okay, so there are no credible accidents that result in an offsite release, okay? Operating plants, they have a lot more things that they have to deal with in order to keep the fuel safe, okay? They have safety equipment. It requires water flowing through different systems in order to cool the system. Then the water has to have pumps, the redundant pumps. Then the electrical systems have to be redundant electrical systems, even backed up by a diesel generator. So it gets all very complicated, and all this stuff is critical to keeping the reactor and the fuel safe. And they have a book this thick of technical specifications that describes what they have to do in order to stay safe. It's, don't get me wrong, it's very well executed and very thorough and redundant, but it's a lot simpler here at the spent fuel facility. So we cool with naturally circulated air. Air comes in the bottom, you've seen this before, it comes out the top. There's no pump, there's no fan, there's no electricity required, there's no moving parts. It's just natural circuit, kind of like your fireplace. Warm air rises, air comes in the bottom, cools it, and goes out. So we only have 2 emergency levels at an ISFC, at SONGS or at any other ISFC. In an operating plant, you have 4. Okay, so when there's a possibility of a release of radioactive material or an ongoing release at an operating plant, they have a site area emergency and a general emergency. We don't have that. Okay, we cannot ever have a site area emergency or a general emergency. Our emergency plan only includes the 2 lowest levels. Okay, so that makes it a lot simpler at an ISFC. Next slide. So why do we use on-site storage? Well, Manuel explained how the federal government has been unable to take the fuel as they were supposed to many years ago. So the industry developed interim storage on site. Okay, notice the terms interim. The interim storage is just what we're using here at ISFCs. It's used at every plant across the country, almost. If they don't have one yet, they're going to have one. I think maybe they all have one by now. It's safe, and it's very closely regulated by the U.S. Nuclear Regulatory Commission, just like operating plants are. I sometimes say it's too safe and too reliable because it takes away the urgency to find a permanent solution. But the NRC is monitoring it and regulates it and controls our aging management program and all the different things that we do there to keep the fuel safe. And they've, said in one of their documents that after 100 years, you might want to think about what you're going to do now, inspect it. But they don't say that there's a 100-year service life. The service life of the canisters could be much longer, especially with aging management. We don't ever want to see it get to 100 years, though, right? Okay. So SONG storage system is designed to withstand the marine environment. Now, that doesn't mean our canisters are setting in a wet spray like the San Clemente Pier. We're here at the beach and the air has salt in it, and we have to deal with that. We assume there's salt on our canisters, okay? But we'll talk later about how salt's just one of 3 or 4 things that you need in order to have stress corrosion cracking. But to withstand the salt environment and the marine environment better, we used special steel 316L. The standard design for spent fuel canisters is 304 steel. We upgraded the 316L. We upgraded our wall thickness by 25%. So we have 5/8 inch walls where the standard design is 1/2 inch walls. And then we have an aging management program at our TN system that's governed by the Nuclear Regulatory Commission. It's required at every SFC after 20 years. It's a program that's approved and by the NRC. There's a book this thick, New Reg 2214. It tells us how to develop that aging management program. And we've executed that at our TN SOC. At our Holtec SOC, that's not required yet. The NRC doesn't require an aging management program until you reach 20 years, and we're only at about 8, 7. But we have a commitment to the Coastal Commission to do the same thing over there. So we're doing what we call an inspection and maintenance program over there, which is the same as an aging management program. It's just got a different name, but it does require mitigation or repair techniques, which I'll talk about later. Next slide, please. This is a picture of our 2 ISFSCs, okay? On the top left is the New Homes ISFSC. Each of those doors comes off, and inside that slides a horizontal canister. At the bottom right is the Holtec ISFSC. Each of those lids come off. They weigh 35,000 pounds, so you have to have either a special crane or rigging to lift them up, and then the canister set underneath those lids vertically. Next slide, please. So this is a slide you have seen before, but I'm going to go through it because it's important. This is the different defense and depth strategies that we employ to keep the spent fuel safe here at SONGS. First is the design, okay? Like I mentioned before, we use 316L. I believe we're still the only plant in the United States using 316L, but that may have changed recently, but the standard design is 304. We use 5/8 inch thick shell, whereas the standard design is 1/2 inch thick. And we're also designed, as every SSC canister is, to be submerged in water. We use some special fabrication techniques. We overrolled the canister, which means we rolled them to a smaller diameter and then opened them up a little bit. That puts a compressive stress layer on the outside and makes them more resistant to stress corrosion cracking, as you're going to hear later. We use special welding techniques. We also peened the welds in our Holtec system with laser peening, which puts a compressive stress layer on the welds. You have to have a tensile stress to have stress corrosion cracking. I'm kind of getting ahead, stealing my own thunder from later, but by eliminating any possibility of tensile stress at the welds, it pretty much makes your canister stress corrosion cracking proof. From an operations standpoint, we monitor for passive airflow. Like I said earlier, all you need to cool the canisters is airflow. So as long as the inlet vent and the outlet vent are open, you're going to have airflow, and it's simple and easy and very, very reliable. For our inspections, we do the aging management program and the inspection and maintenance program over at the Holtec SOC, and the guidance from the NRC, New Reg 2214, is to focus on the oldest and coldest canisters, and there's some more guidance like that. It's very well controlled and orchestrated, the inspections. Now, remediation is something we have that nobody else has. The Coastal Commission has asked us to develop remediation. We have. We developed a metallic overlay, also called in the industry literature cold spray. We've developed it, tested it, proven it. We have a test canister, which most plants don't have, and we demonstrated it in the field on our test canister. And once we demonstrated it, then we did maintenance on it, put it away. It's on the shelf, ready to go, and that's for the Holtec system. We also demonstrated it for the TN system, and we have that on the shelf, ready to go. Next slide. So I'm going to go through cask versus canisters again because we keep getting questions on this. So these are two pictures of two different cask systems. Okay, the one on the left is the U.S. system. The one on the right is the European system. A cask is a thick, heavy, durable container that provides shielding and protection from the elements. For example, tornadoes. Tornado missiles, they're both protected from tornado missiles by the very thick and robust cask. Okay? A canister is a welded sealed system that goes inside a cask that seals the fuel from the elements and relies on the cask in order to provide the protection and the shielding. Okay? The European system on the right doesn't have a canister. All it has is a cask. It seals the cask and uses the cask to provide both the canister function and the cask function. The European system is a bolted head system, and it was developed because they do something in Europe that we don't do here. They reprocess fuel. It's still illegal, although that may change, but right now we cannot reprocess fuel in the United States. Who knows what will happen in the future? But the bolted lid makes it easier to take the fuel out when they need to reprocess it. They put the fuel in here, they transport it to the reprocessing facility, they take it out, they do their business, okay? So that's very convenient. But in order to do that, it has to be a little bit lighter. So they don't have as much shielding as we do. We would not be happy with the amount of shielding in the European system. That said, it's adequate for what they need, and it works. Both systems are good, but ours is heavier. Ours can be heavier because we don't have to lift it with a crane. We lift the canister with a crane, but the cask doesn't have to be lifted with a crane. So we get a lot of benefits from having the canister and the cask separated. They don't need those in Europe, and they focus on the reprocessing. Okay. Why does the canister on the left, though, not look like San Onofre's? Okay. Most of the ISPACs in the United States are going to have a cask like the one on the left, setting out on the pad. You'll have a bunch of cylinders sticking up like that. We chose the New Home system because it provides even better shielding and a more robust protection, whereas this cask on the left is maybe 12 to 18 inches thick. We've got at least 2 feet thick of concrete protection to provide extra shielding and extra protection because our cask is integrated into the structure. Same with the Holtec system. The cask is integrated into the whole big concrete mass that surrounds each storage location. So we've got up to 10 feet of concrete out at the Holtec system protecting the fuel. So, bottom line is they both provide robust shielding and missile protection, but we couldn't use the we wouldn't want to use the European system in the United States. It's not licensed, but even if it were, we need at songs at least we need the better shielding. Next slide. So our inspection methodology. So the NRC requires an AMP after 20 years of service, and the New Home system has gotten there. Over at the Holtec system, the California Coastal Commission said, go ahead and start now. So we have an inspection and maintenance program there, even though it hasn't reached 20 years. Both programs use the same methodology. They're almost identical. We developed our inspection and maintenance program using the same guidance from New Reg 2214 and the EPRI documents as we did for our aging management program. Both of the programs require that we inspect two canisters every 5 years. And as far as what we've inspected so far, we've inspected 10 in the UMAX and 2 in the New Home system. So we've inspected 12 canisters so far. Next slide.
Excuse me, Jerry, we have a question from Martha.
Okay, Jerry, I should know this. I've been involved with this for years, but remind me again, New Homes and UMAX, which one is the Holtec?
Sorry, I should have been clear. So UMAX is the Holtec.
Okay, and that's the horizontal one.
No, that's the vertical one.
That's the vertical one.
The horizontal one is New Homes, which is also called TN, also called Arriva, and also called Arano.
Okay, and they were first.
They were first. They're 20 plus years old, and we're in an aging management program.
Okay. I've heard the words forever and ever. I sometimes need a little reminder.
Thanks. Good review.
Thank you.
Thank you for that. Okay, so we at San Onofre are proud that we developed the inspection technique. So in 2019, when we went to inspect these canisters, there wasn't an inspection robot available. We went out and contracted with Robotics Technology of Tennessee, who's now the industry standard for doing inspections. We contracted with, at the time it was GE, now they're IAG, the company, you know how companies change names nowadays. They're now the industry standard for doing all the inspections. And we put it all together. We also added the cold spray to the same robot. So we put all of this together in 2019 to go do the inspections. So we were the first people to put it together, and almost exactly like we did it then, it's become the industry standard. So we got 2 high-resolution cameras on the robot that, by having 2 cameras doing 3D like your eyeballs, it can actually measure the depth of a scratch, the thickness of a leaf. You know, it can measure any dimension to a thousandth of an inch. Okay. Very, very high resolution. Okay, so stress corrosion cracking. That's what we care about. That's what we worry about. Stress corrosion cracking is the failure mechanism that the industry is looking for in a canister. It's never been seen in a canister anywhere in the United States, and I don't believe anywhere in the world. We don't have as great a data about worldwide, but we don't believe it's ever been seen anywhere. But we know what it looks like. We've done a tremendous amount of lab experiments. EFRI's done a lot of work, and we know what to look for. So I brought this picture, since you're going to be looking at 1,749 pictures, I brought this picture of what does it look like, okay? The dark brown spots, especially, let me see if I can find the right button. There we go. That spot right there, see how dark brown that is? That dark brown is the kind of the trademark of stress corrosion cracking. That dark reddish brown is what we're looking for when we go look into these pictures. And of course, we hire experts. We have a team of people looking at it when we do the inspection. But what we're really looking for is the dark brown corrosion products. Okay. Now, to get CISCC, and I think you're going to hear this several times tonight, you have to have susceptible material, you have to have a tensile stress, and you have to have chlorides. In this case, what it says here, sea salt brine, what that means is chlorides. The chlorides have to be wetted. They can't be dry chlorides. We have dry chlorides on all our canisters, okay? There are dry salt on all our canisters. In a seaside environment, you're going to have salt everywhere, okay? We don't try to prevent salt. Just want to make that clear. Said it 3 or 4 times. We don't try to prevent salt. What we do prevent, though, is wet salt, okay? You're going to see that our canisters are dry as King Tut's tomb. I may repeat that because that's the way I like to describe it. So as long as the salt can't get wet, you cannot have stress corrosion cracking. If you don't have tensile stresses, you cannot have stress corrosion cracking. If you don't have susceptible material, you cannot have stress corrosion cracking. Now, 316L is susceptible, but it's much, much less susceptible than 304. So we chose a much less susceptible material. It resists stress corrosion cracking a lot.
Terry, could I ask a quick question, please?
Yeah.
What's the difference between this and just plain rust?
Well, this is just plain rust. You don't get much just plain rust on stainless steel.
Okay.
You might get a surface layer of oxide, and we do see that on our 304 stainless in the field. But stress corrosion cracking, the difference is that it has tensile stresses causing cracking, and those cracks go subsurface. They'll go clear through the pipe. Rust, on the other hand, would just have to work its way through the pipe over the years.
Okay, thank you very much.
Okay. So the last point I want to make here is that most of the canister shells not susceptible.
I'm sorry, we've got another question. John?
Okay, I'm sorry, go ahead.
Can I just ask an engineering question? Where does this tensile stress come from?
Oh, good question. Thank you. So leads right into the last bullet point here.
Okay.
So welding creates tensile stresses. Okay. I told you we overroll the canister and create a kind of a compressive stress on the outside layer, except where you have to weld it. So the canisters are made from plates that are rolled into a circle and then weld. They have one long weld down the down the horizontal. They have one belt line weld around the middle, okay? So those weld areas are the susceptible areas. They have the tensile stresses, okay? And in the Holtec system, we used peening. I don't know if you're familiar with shot peening. Nowadays, instead of shot peening, where you'd fire BBs at it to peen it, now we used a laser to hit it with 1 million laser pulses to create compressive stress layer at least 2 millimeters deep on all our weld areas.
And the cameras are able to see all of these welds when they go in to inspect?
Absolutely. That's the requirement of the code to inspect all the welds.
Okay, thank you.
So I think I covered that last bullet. Next slide. Okay, so now I'm going to talk about what you're going to see on the photo. So this is where I want to remind you that if you've zoned out a little, you'll want to pay attention to this. Okay, the first picture up there is what we're calling fabrication marks. So the steel plate that canisters are made out of has got kind of a rough surface. It's not smooth. It's got a kind of a surface kind of like sandpaper, okay? And it comes across kind of white on this picture on the left. But there's places if they go out and if they have a weld, all the welds are buffed smooth, and they're kind of shiny and they come across dark. If they have something else they want to buff out on the canister, it becomes shiny and it comes across dark. So that rectangular area at the top of that picture on the left, that was buffed out and it became shiny, okay? On the right, you'll see a magic marker number.
Excuse me 1 second. Victor has a question.
Go ahead.
These are obviously magnified. Can you?
Not a lot.
Not a lot? Okay.
Not a lot, no. Yeah, we have some that are up close. We have some that are open pictures. In order, the buffed out area there, that may be 2 feet wide.
Okay, all right.
Yeah. And these numbers is 6G, that may be 3 inches high. We don't know for sure how high it is. But those would all be made with a low chloride marker, although it doesn't really matter now that we got them out here where there are chlorides. But that was something that just helped them to fabricate it. Next slide. Oh, this is one of my favorite pictures. So the Holtec canisters, all called DSCs, have a lot of dust up on top of them. How did dust get there? It floated on the air. So we don't have dust like you find on the road, which has sand and rocks and all kinds of things in it. We have dust that can float on the air. So everything you see on the top of a canister floated there on a cloud of air. It's very, very fine. It's like talcum powder. It's stuff that can be easily transported. So this is some really, really fine talcum powder type dust. And it's the same, by the way, these pictures aren't color, but if you see it, when you see it in color, it's the same color as the road on Old Man's Beach. So there's that.
Horizontal system, right?
Yeah, this is the horizontal system. So up on top of the horizontal system. So the robot driving around is held to the canister by a vacuum. So it pushes the dust in front of them, so like a snowplow. So what you see there is the piled up dust that was pushed up by the snowplow effect of the robot. And the dust is just very thin, maybe 30 to 60 thousandths, a 16th of an inch, and that pile is maybe an eighth to a quarter of an inch tall. So it's not very high, but it's piled up and it's all dry. It's all very, very loose. It's I think it's an incredible condition. There's no signs of water intrusion on these canisters, the dry storage canisters from TN. Next slide. Okay, now we're looking at the Holtec MPCs in the vertical system. On the left, we have free iron transfer. And on the right, we have rub from the shield ring. So remember, the shield ring is up at the top. It's a ring that prevents streaming of radioactivity out when they're loading the canister. It's very thick steel, and it's only a ½ inch bigger in diameter than a canister. So the canister is 76 inches diameter, the shield ring 76.5. So it's a tight fit, and as it goes down, it can rub. It's painted with a zinc paint, and that can come off onto the canister. And sometimes all the zinc rubs off, and you might get a little free iron transfer from the shield ring. But the shield ring rubs are always going to look like that. They're going to be wide and have kind of vertical lines on them. Free iron transfer. I don't know how much we've talked about that before. I think we did talk about it when we talked about canister 72 before, but I'm going to go through it again. So when we process these canisters, they sit in a cask, okay, the transportation cask, which is like that cask I showed you earlier. That's thick, it provides shielding, and it provides protection from the elements. But while they're in there for processing, they're also in a jacket of water. So there's about 2 inches of water all the way around it. Sorry about that. So so this water separates the canister from the cask, and it's about this far apart. Okay. Well, the cask has an epoxy coating on it. It's carbon steel, but it has an epoxy coating. Unfortunately, the cask that we were using, that we rented from Holtec, had a hole in the epoxy. So there was some carbon steel showing, okay? So that carbon steel rusted. So now it sits there for about 2 days. We have to weld the lid on, we have to take the water out, we have to vacuum dry it, then we have to seal weld the ports. So it's about two days, maybe longer. And while it's sitting there for those 2 days, with this rust here and the canister there, ions in the water transport themselves across that 2-inch gap, and they affix themselves to the canister. So there's some iron, what we call is free iron, that's been transferred from the cask to the canister through the water. Okay, it's on the surface. It's not a sign that the canister's rusting. It's iron particles on the surface that came from somewhere else. Okay, and that's called free iron transfer. It's been discussed a lot in the industry. It's been debated in a lot of different committees, and I'll talk a little bit more about what San Onofre did in order to kind of settle the discussion on free iron transfer in a minute. Next slide. Okay, these are scratches. Okay, there's lots of scratches. The scratches are all vertical. Okay, they all happened as we lowered it in. So something that mostly the seismic support rubbed, and so the scratches all became vertical within a few degrees. The pictures may show them at any angle because the robot can be tilted at any angle. The robot doesn't go on a programmed route. It drives around and looks at things, and so it could approach things from any angle. So we get all kinds of angles. On the right, we're doing a surface profile of a scratch. That's, I talked earlier about how the robot can measure to 1/1000th of an inch. Well, that's what's happening there on the right. It's measuring the depth of the scratch to 1/1000th of an inch. Okay? And that scratch is 12/1000ths of an inch deep. You can read that on this slide. And there's the surface profile generated across that scratch on the right. One thing I want to say, whenever you see the term surface profile, ignore the colors. In this thing, it's kind of bright and luminous. Sometimes it's green, sometimes it's brown. One of them looks like Jupiter, and the colors get greatly exaggerated, or sometimes just fictitious color gets added. Use pictures that do not have surface profiling done in order to evaluate color. Next slide. Okay, water intrusion. Okay, so on the right picture, that's the original outlet vent covers. Okay, those are screens that are vertical screens. They sit there, and if the rain comes straight down, no water gets in. But does rain come straight down here? No, it blows, right? So when blowing wind happens, it blows a little rain in. So we called Holtec and says, hey, there's rain blowing in. And they said, well, that's normal. And we said, well, we'd rather not have rain blow in. And they said, well, that wasn't the design. A little water won't hurt anything. It'll just evaporate. And we said, yeah, that's right. And that is right. So on the left, just look at that water intrusion. That all came in during a rainstorm. It ran down the side of the canister, and it dried up quickly because the canister's hot. The canister's got fuel in it, and the surface temperature's warm, and it evaporates the water. And within hours, it's dry as King Tut's tomb again, right? So the it's really not a problem, but it isn't very pretty. So, and we didn't like the idea of that happening for however many years these canisters have to be here. So we installed the new outlet vent covers in the bottom center middle. Those outlet vent covers prevent wind-blown rain from entering the screens and keep water from getting in on our canisters. It's not required. There's no analysis that requires it. The NRC doesn't require it. We just proactively installed those. Next slide. Okay, this is a RT mark. So all of these canisters were fully radiographed when they were fabricated. So they had to take, and they take a radiograph, scoot over 12 inches, take a radiograph, scoot over. So in order to remember where they're at, they put a lot of little punch marks all over the canister like these. And you'll see them when you drive around. And so I just wanted to let you know that that's what these are. There's a lot of them there. Most of them we don't have a picture of. When we went in to do our field testing of our mitigation system with cold spray on our test canister, we actually found some of these and covered them up with cold spray. That was one of our tests that we did. Next slide.
Transition with the next one. It's a good transition with this one.
Yeah, and here's our remediation robot. So the ASME code says if you're more than 10% of your wall thickness, yeah, that's in this case that's 62 thousandths, a 1/16 of an inch. You need to consider doing remediation, which means you need to do engineering evaluation or to go and do some remediation. And of course, we have an extra 1/8 of an inch, which we can certainly take credit for. So, our evaluation of a scratch wouldn't be so much concerned about the depth of the scratch, because the depth of a scratch is never going to approach a technical issue. It's more about what caused the scratch. We're more interested in what would have caused the defect. I say scratch, but there's lots of different defects that could cause it. But our scratches, the deepest one in the Holtec system, 16 thousandths of an inch. There's slightly deeper one in the TN system. But nothing that's even approaching the 62 thousandths of an inch. We also had a test canister that we practiced with when we were getting ready to do the GTCC project at the TN system. And we put it, and the iron workers doing their thing, put it in and out like 50 times. And the scratches never did get more than about 15 thousandths deep. So that was really good to see that repeated insertions and removals doesn't cause the scratches to grow. So for stains from the free iron transfer, and I'll talk about this a little later, we looked for change between inspections. Okay, on canister 72, we inspected it in 2019. It had a free iron transfer stain on it that looked kind of like North America. And we went back in and looked at it again after 5 years. And every bit of it, you can look and it hasn't changed from picture to picture. And that was really good. I think we got a picture of that later. Streaks from the rainwater are not an issue. I already talked about how it dries on the warm canister and our canisters stay warm and dry. And then the cold spray, we developed the cold spray songs, and we're the only people in the industry that have it. And ASME is working on a code case to make it an official method to repair. In the meantime, if you were to use it, you'd use a 7248 evaluation. Next slide.
I think that was the last one.
Yep.
And that's it. Well, that was enough for me.
That's a lot. Thank you, Jerry. I want to turn and see if there are any questions from anyone. John?
Yeah, do those scratches induce stress?
Well, they definitely induce some compressive stress as they push in. At the edges, we can't say that they don't induce some tensile stress, but we have inspected and we haven't seen any signs of any initiation of stress corrosion cracking. But yeah, I wouldn't be able to say that there's no stress associated with the scratches.
Okay, thank you.
Here, Dan, I got a question. The approximate size of the canisters, I understand they're about 16 feet tall. How far around? It's
A little over 6 feet, 76 inches in diameter,
70, okay,
or
in diameter.
3 times 6, 18, about 19 or 20 feet in circumference.
So 19 or 20 in circumference. I guess that's top to bottom. Okay, but
That's around.
that's around.
Yeah.
19 feet.
Yeah, pi times diameter.
Okay, all right.
And how much do they weigh?
About 100,000 pounds. Randall, can you answer that? 100,000 pounds plus the fuel is 200,000?
Okay, a lot. 90,000 to 100,000 pounds. So, okay. Pretty hefty for sure. Okay, looking to see, I don't see any other questions either here or online. So once again, Jerry, thank you so much. And now we'd like to turn the floor over to Dr. James Burns. Dr. Burns, thanks for staying up or getting up early. Hope you've got plenty of coffee or Red Bull there for you. The floor is yours.
Yeah, excellent. And I'll be able to share my screen. Is that correct? Is there a problem with that?
I'm sorry, could you understand it?
I didn't catch that.
Say it again, please.
Is he going to?
Will I be able to share my screen?
That's correct, Jimmy.
Got it. Okay, great.
Thank you.
All right. Excellent. Is that, can everybody see this okay?
Yes.
Yes.
All right. Great. Well, I appreciate the opportunity to chat a little bit about this. I'm Jimmy Burns. Today I'm speaking on behalf of my consulting company, but my day job is a professor at the University of Virginia. I appreciate the introduction before. Just give an idea of what I'm going to talk about today, okay? So I want to kind of give a bit of background. You know, I think Jerry did a really nice job of speaking specific to the canisters in the site. What I was going to do is blow back out a little bit and provide a bit of context just of the damage mechanism and the damage mode. So I'll kind of talk about those fundamentals. Then I'll talk about the origin of the contributing factors in general for this application. I'll go in, you know, several times he had mentioned the management guidelines, and I'll go into a little detail and provide the background for, you know, what the justification and what the documents are that actually guide the protocols that they use in this aging management plan. And then finally, just have some commentary on all of the bullet points above on how that then informs kind of proper evaluation of the inspection results. So I like to do this right off the get-go. You know, I'll talk about these things, but I'll tell you the answer ahead of time. I'm a professor, so I'm giving away the answer to the test. But the takeaway from regarding the origins of the contributing factors, CISEC is going to require sufficiently severe microstructure stress and environment. I'm going to say that several times. The presence of those three things are necessary, but not sufficient condition in order for CISEC to happen. The inspection, and because of that, the inspection indications in the weld regions are really the only ones that are going to be relevant to the CISEC. So seeing inspection indications, if they're not by the weld region, the CISEC just simply can't happen. And then there's a decades-long window, as was alluded to before, an environment that would support CISEC should form. And then finally, relevant to the management guidelines, it is a mature and rigorous aging management program to ensure safety. There's been a extensive amount of work looking at this damage mode, looking at how it progresses, looking at potential environments and all of the different factors that go into driving this environment to try to understand the extent to which this may be a challenge that needs to be addressed. And then also then how to repair that if we do see something. So let's hop into it. So what is stress corrosion cracking? Kind of the textbook definition that I'm sure nobody wants to hear a professor talk, but the textbook definition, it's some crack formation and stable growth below the fracture toughness that's caused by a time-dependent damage mode in the conjoint interaction of environment, stress, and susceptible microstructure. Okay, and so that is our damage mode. We need all three of them. And so, as I said before, just having all three of them is necessary, but not necessarily sufficient to be able to cause this damage mode. So each of them must be above some certain severity level to be able to kickstart this process. So let's use an analogy here. Okay, let's say stress corrosion cracking happening is like driving a car. All right, there are three things, a bunch of things, but let's just simplify it down. To drive a car, you're going to need engine, you're going to need wheels, and you're going to need gas. And those three things, if you don't have gas, you can't drive a car. If you don't have wheels, you can't drive your car. And if you don't have an engine, you can't drive your car. And so point number one, all of these three things are necessary. Point number two is each of these three things need to be sufficient. And so that in stress corrosion cracking, it's a sufficient level of severity of the environment or stress or susceptibility of the microstructure. Using our driving a car analogy, if I only have three wheels, I have wheels, but I don't have enough wheels to drive the car, right? Thinking about the engine, if I'm trying to drive a car and I have an engine, but it's just a lawnmower engine, I'm not going to be able to drive my car. And if I have gas, but it's 50% water, that gas isn't sufficient to be able to drive my car. So not only do I need these things, but they have to be sufficient at a sufficient severity to be able to be functioning in this instance, drive a car, or in the technical instance, produce stress corrosion cracking. And then finally, as one be expected, if you have a car and you have a bigger engine, then it could go faster. So for example, in stress corrosion cracking, if you have a higher stress, that can drive things to go faster. Or if you have premium gasoline in your car, it can go faster. And that's the same thing in stress corrosion cracking. If you have different environments, can give rise to different rates of cracking and susceptibility to cracking. So why are we even looking at these? And so when we look at these, the chloride-induced stress corrosion cracking has been identified as a possible relevant damage mode. And so these are just some documents from the NRC, Nuclear Waste Technical Review Board. As during these applications, it was something that was identified as something that should be concerned about, and to the extent to which we need to look at it and develop a plan to be able to have to manage it and expect it and just better understand it and study it. And so if I say that these are the conditions that are necessary for chloride-induced stress corrosion cracking, and it was something that we wanted to look at for this application, then what are the sources of the susceptible material, stress or environment? And so the type of materials that are used in these applications are called austenitic stainless steels. Okay, and specifically, as was mentioned previously, 316L is the specific application for the relevant to the meeting today. And so these have been shown that under given environments and at a sufficient level of stress, that they can be susceptible to this damage mode. And so this is a growth rate versus some mechanical driving force, and this just shows that we can get cracks to grow. As Jerry alluded to before, different materials have different levels of susceptibility, right? And so 304 is growing faster, and so that has a faster growth rate. And as he said, if you do have that stress and you do have that environment and they are sufficiently severe, you can get cracking. And if you do get cracking, then it cracks slower in 316 than it does in 304L. So for this low temperature cracking mode, right, and we consider this low to intermediate temperatures, the temperatures that we're talking about here, as compared to some of the other work that maybe you would find in the literature at higher temperatures relevant to actually in reactor sites. The crack morphology is often what we call transgranular, then it can show significant amount of branching. Jerry showed that in his slides earlier, to where you had a significant amount of branching. It wasn't a single crack front running forward, and that's somewhat typical of this damage mode in this material system. Now, remember how I talked about, the extent of susceptibility can depend on the details. Like different materials can crack at different rates, and that susceptibility on materials, it depends on the details of the material composition, the extent of what we call cold work, and so that's the amount of dislocation or plasticity it's put into it that kind of correlates to the strength of the material. It can depend on the weld microstructure, a phenomenon called sensitization, and microstructural orientation. So there are details of the material that impact how susceptible it's going to be to this damage mode. And so the thing I want to take away from this discussion, so we just kind of summarized of the three factors: susceptible material, stress, and environment. Talking about susceptible material, these stainless steels, it can be susceptible to CISCC. But as I said, only if there's sufficiently severe stress and environment. Now let's look at the stress level. It was great. There was a question earlier about the genesis of the stress and where it comes from. And so, this has been studied. So there's been modeling and experimental studies to be able to look for this specific application, where those stresses will come from. And where they come from is something called a weld residual stress. And the reports that have studied this have suggested that this is really the only sort of stress that's going to be sufficient to potentially drive this damage. Now, what is a weld residual stress? Let's just take a second and talk about what a weld is, okay? And so let's just say this is a cross section of the plates of steel that is creating the circumference of the component of the MPC. Well, that you have to join those two plates of steel together. And this is just an example of how you might weld to join the two steels together. Okay, so the teal here are the plates of steel. You would have pass number one that would be the green, pass number two to where you actually put a weld bead down. You would add a weld bead to pass number two, and then just build up from there. Okay. Now, due to the thermal gradients, so welding is obviously hot, right? And then it's cooling down. During the thermal gradients that happen during the welding, you can get a residual stress profile just intrinsic to the material system. And so just sitting there, you can be under a stress due to this weld residual stress phenomenon. So there's steps you can take to be able to minimize that. But it is a phenomenon that can happen. Now let's just kind of slow down here for a second and take a look at this plot here. So what this is plotting, and so hopefully everybody agrees with me, can y'all see? Y'all can see my pointer here. Where I'm pointing to right here is the center of the weld. Okay, so that's the weld center, right? What this plot is pointing, the zero position is the center of the weld. And then on the y-axis is then the residual stress. And so what this shows is from the center of the weld going out, your residual stress essentially goes to 0 1 inch away from the weld center. And so 1 inch on either side or 2 inches surrounding the weld center is the only place where you have a residual stress field. Okay, and so this is data, and it's, the details of how it was generated or can be found in the reports. But so what? What does that mean? Well, if we look at where those locations are on the component, the only place that there's a driving force for this CISCC damage mode to happen is going to be directly adjacent to these welds, because there is no stress, there's not a stress that can drive this damage mode anywhere else besides directly adjacent to the welds. Okay, and so this is an extremely, I think we just talked about how big these components are. This is an extremely low percentage of the surface area. And so it's really important to recognize this when you interpret the relevance of your inspection findings, because here's our weld region, right? It's kind of color coded here. And then this is expanded here. And these dashed lines represent kind of a 2-inch, that 2-inch example I just showed on the last slide. And the only place that CISS is possible, or CISEC is possible, is in this region here. And so interpretation of the inspection results relative to where they are by these weld residual stresses is very important. So the takeaway from this little discussion is weld residual stress can provide a potential driving force for CISEC, but that's only in a very few locations. And it's also, remember what I said before, just because there is a stress, so you could have stress here, you could have an environment, and you could have a susceptible material, but just because there is a stress doesn't mean that stress is sufficient to cause CISEC, okay? And then the final component that you need is an environment. So the environments aren't underwater, so these canisters aren't underwater. So where does the electrolyte come from? And so we alluded to that, Jerry alluded to this, but there's various different ways for aerosols to be generated, okay? And kind of a primary generation of the aerosols is going to be sea salt or something that is carried through the air, okay? And so we can have those, and a lot of our storage sites are by the coast, as is the one in question here. Those aerosols, the way that that these are generally cooled, this is just a schematic of what Jerry described earlier, is you have a flow of air that comes in and cools the canister, and then cools the component and then flows out, right? And so aerosols that are in the air are obviously part of this passive ventilation system, and can they then deposit on the surface? Well, what does that mean? Well, just the fact that solid salt is deposited on the surface is not an electrolyte, or is not sufficient to be able to create the environment in and of itself. And so a process called deliquescence has to occur in order to form an electrolyte. And so deliquescence, what is that process? Well, you would have a solid salt. Let's just say, have a example here. You just have some solid aerosol salt that lands on the surface, dries out, and you just have a solid salt. At sufficient relative humidities and low enough temperatures, that salt can start absorbing water. And if you have a sufficient relative humidity, it can completely dissolve and create a solution. Okay, and so just as a silly example, folks would be, familiar with is, if you come out to your car after a snow day, or there's some salt or something like that on your car, you can get kind of a thin film of electrolyte or wetness. Okay, and so it's probably something that all of us have seen and not even noticed, but this is kind of the underlying thermodynamics behind that. Now, the extent of that deliquescence, right, and this is just a plot that nobody worry, I'm not going to go into the details of this plot. I just want to show it as an example. But the deliquescence, this process, is going to be dependent on the relative humidity, the salt type, right? Is it NaC, sodium chloride? Is it magnesium chloride? The salt type, and then the temperature, right? And so, this is something that has been studied and reported. And then the electrolyte volume and the composition is then going to depend on how much salt has deposited and the relative humidity. And so again, this is examples of that is shown here, to where your ion concentration, or your concentration of your salt, is dependent on the relative humidity and the salt loading density. And so the reason that this is, I bring these up and I show these plots, is that just to show and give an example of the depth of study that has been done to be able to try to understand this damage mechanism and the propensity for this damage mechanism to happen. So again, these are just examples. I've just pulled out a couple of charts from a report from Sandia National Lab. One of the things that is happening over the course of time is your the fuel, okay, is at an elevated temperature. It's cooling down. That's why it's in there. And so that cooling, that the fact that it's in an elevated temperature makes it such that the surface of this component is actually at an elevated temperature, right? And so this is just an example. So this is temperature versus time, right? So for a couple of sites, and details will be in the report, but this is just shown for example purposes. The temperature is decreasing with time, right? And so that temperature is going to be modifying the humidity. Okay, and so this is just runs for a variety of different example cases. As I said, the details are in the report. Well, let's just say you need a relative humidity 30% for this deliquescence process to happen, right? So remember, we talked about the deliquescence. You need a certain level of humidity based on the salt type. Let's say you need a 30% relative humidity. So in this instance, even kind of in order to get there, it's going to take a significant amount of time, right? So the worst case in this example, there'd be no deliquescence on order of 30 years, just simply because the canister surface temperature is too high to be able to thermodynamically support that electrolyte. Now, again, we're talking about necessary but sufficient, right? Let's say an electrolyte does form, okay? Just because an electrolyte does form does not mean that CISCC is going to happen, right? So you could have a susceptible material, okay? You could have a stress, and you could have this environment, but that doesn't necessarily mean that you are going to have CISCC. It can happen. Those are the things necessary for it to happen, but it doesn't necessarily mean it's going to happen. And so the extent to which CISCC, the susceptibility, that's going to be dependent on what is the electrolyte composition. What is electrolyte volume? What's the temperature? What's the time of wetness? How often is it wet? Okay, and so this is just an example, again, of crack growth rate. Earlier I showed it for two different materials. Now this is just an example of crack growth rate. First, that driving force, mechanical driving force. And this shows there's a very important dependence on temperature, right? And so it can crack faster at higher temperatures, and then as you decrease temperature, you can go down to where actually you don't see any susceptibility, okay? And so what's of interest is you have kind of a sweet spot of temperature, right? At very high temperatures, you can't get an electrolyte because it's not thermodynamically stable. Well, once you get it, then as the temperature continues falling, as during the course of operation of these components, it starts to decrease the crack growth rate, or decrease the susceptibility or the intensity of this chloride-induced stress corrosion cracking. So what are the takeaways we have here, okay? CISCC, it can only happen if there's an electrolyte. So we said these aerosol, salt deposition, and deliquescence provides a means by which to form an electrolyte. Due to the elevated temperature of the surfaces of these components, there's a long time window to where an electrolyte would not be thermodynamically stable. If the electrolyte does form, when it does become stable, then the severity of this damage mode depends on the volume, the composition, and volume composition of the electrolyte and the temperature. And in some ways, there's kind of a self-regulating dependence on temperature. So at high temperature, you don't have an electrolyte, but as your temperature continues to fall, when you do get an electrolyte, if it continues to fall as you decrease that temperature, the growth slows down. All right, let's switch gears a little bit. And so those are the things that you need, right? Now, what are the relevant guidelines that govern the management of this? And so, as I said, there's been a lot of work that went into developing these approaches. And so we mentioned the new Reg 2214, and then this is a ASME code case that lays out how you need to kind of manage and perform the inspections and provides the guidelines for the aging management plan. And one thing to note is it is a continuing evolving process, as any aging management process should be, or program should be. And so indications of that is there's, we have learned things and done a lot of research over the last 10 or 15 years, and that's being integrated by the NRC to update and provide new draft regulation guidance. And so it is a dynamic and a learning environment that is responsive to the inspections. One other thing to note is that there are aging management plans to be able to manage stress corrosion cracking in various industries. This is the fact that this damage mode can happen is not something that is unique to the nuclear industry. The aerospace, marine, oil and gas industries, that this is a damage mode that's well known, that people think about, and you're using metals in aggressive environments and in many different applications. So this is a damage mode that people have to deal with. So the fact that there's this aging management plan within the nuclear community for this application that is consistent with other applications. So let's briefly, I'll kind of align this talk and kind of finish up with okay, why did I talk about these things? Well, I think that these details provide a little context for interpretation of the inspection results, right? So CISCC is only going to occur for sufficiently high material susceptibility, stress, and chloride-containing environments. A feature must be in a region of residual stress in order for CISCC to be possible, okay? And so that is being in that region is necessary, but not necessarily sufficient condition to be, just because you find an indication inside a weld region does not mean you're going to have CISCC. You would also need a sufficient level of stress and an electrolyte for that to happen. We are the most interested in corrosion pits, more so than scratches or something like that. And the reason we're interested in corrosion pits is because that gives us an indication that there is potentially a electrolyte present. And then in addition to just the local stress concentrator, you can also have a chemistry development at the base of the pits that is going to be more conducive for initiation than would be a scratch or a gouge or something like that. So the scratches and gouges aren't necessarily potent initiating factors for this damage mode, or as potent initiating factors for this damage mode. The deliquescence of salt deposits, it can only happen at sufficiently high relative humidities and sufficiently low temperatures, right? Just thermodynamically. And so the elevated temperature on the canister, that can preclude an electrolyte formation. And if stuff does get wet, as Jerry showed for the blowing rain ingress, it would quickly dry. That moisture would quickly dry on the surface. And then lastly, there is a kind of a multi-level and conservative aging management protocol that's in place and it's guided by the federal guidelines. And, I think that as I've been talking, I haven't been really highlighting this, but there's been kind of screenshots of images of report covers. And those are just a sampling of kind of the extensive documentation and justification from looking at the industry participants, like at EPRI, from the government and academic literature. And so that aging management protocol was developed in the context of developed and then continuing to be improved in that context. And so there's avenues for this continuous improvement and responsiveness to inspection results. And this is managing stress corrosion cracking happens in many disciplines. Finally, if all does go wrong, if the damage is found during these inspections, and there are repair, I didn't talk about this a lot, but there are repair approaches that are available to be able to address any sort of indication of chloride-induced stress corrosion cracking. So with that, I can stop sharing and pass it back to the organizers.
Well, thank you very much, Dr. Burns. I think that was very insightful. I know, especially for me, when I took chemistry many, many years ago, it was always temperature seemed to move reactions faster. So when thinking, I always thought, well, if it's hot, the chemical reaction is actually going to take place quicker. But actually what you're telling us now, that if, at least in this case, that that's just the opposite, that as the temperature drops, that increases the likelihood. It's just one of the many factors that has to be there for the corrosion to actually take place. With that, I'm going to turn. We've got a couple of questions here. John Taylor, please.
Yes, thank you, Dr. Burns, for that explanation. I think one of the concerns of most of the public, given the location of the ISFSI and sea level rise, is that a large wave of some kind would inundate the canisters to the point that there would be electrolyte in the compartment. So if that was a possibility, and I would say it maybe not likely, but it is possible, and that's what people are concerned about, I think, what would be the procedure to, stop this corrosion if that were to happen? If you could hear that.
Yeah.
So the.
Want me to take that?
Yeah.
Yeah. So while the canisters were flooded, the water would provide cooling, but you need to get them back to a dry condition, right?
Right.
So we would have plenty of time while they're cooled with the water to plan for a way to evacuate, dry them, clean them. Remember, they are warm, so they will self-dry. All you got to do is get the water out, let them dry their surface. Then once again, we already have salt on the canisters now. We assume we have salt. Electrolyte is salt water, right? So once they warm up, the water evaporates off the surface. They're dry and back in a stable configuration.
And just so Dr. Burns, you would concur with that as well? Yep.
Yes, I would concur with that.
And what about washing them with, clean water? Would that be necessary to do something like that?
Probably.
Yeah. Okay. Thank you.
Thank you, John. Thank you, Jerry. Looking around, any other questions? Seeing none, I want to thank you once again, Dr. Burns, and thanks for hanging in there. I know you're going to be there. We probably will have some questions from members of our audience that are calling in. So once again, thank you. And with that, we're going to move on with our next item on the agenda. And next, we're going to have Jerry back again, and he's going to review some of the inspection images. And I understand these images were selected because they were the ones that were of interest to the general public. And that just to remind everyone, these are just a sampling of the photos of each inspection. But if you want to go there, there's 1,749 of them that are available on the website.
Okay, thanks. Okay, I've been told to move it along, so I'm going to try to hurry here, but I'm not going to skip any material. So next slide. Okay, so all the inspection images are on the website. We're going to give you a link to that in pretty soon. We document a tremendous amount of observations. You'll see the tremendous detail. Very few pictures of nothing are on there, and I might try to change that in the future. But all the canisters are in good condition and nothing that requires repair or mitigation. Next slide. Okay, now we're going through the images. So first image. Oh no, we're going through this. Okay, so this is MPC 72. Okay, this is the free iron transfer that I told you looked like North America. Maybe that was an exaggeration. But on the left is the 2019 image, on the right is 2024. They look almost identical. If anything, the image, it looks like it might have gotten smaller in 2024. So remember I told you that this free iron transfer had been debated and discussed in the industry, thoughts about whether we needed to go and clean it off, remove it, mitigate it. And when we saw that it had absolutely not changed in 5 years, there was a lot of exhalation. Everybody says, it looks, it's very stable. We see no reason to go and do anything with it. So we'll continue to monitor this. We have these stains on many canisters, and we'll be monitoring more of them in the future. Next slide. Another picture of the same image from 2019 and 2024. Next slide. This is a scratch, okay? So scratches are, like I said, they're all vertical. This is just one of the scratches on canister 72. Next slide. More scratches on canister 72. On the right is a characterization. We call it the surface profile of the scratch on the left. It's 15 thousandths deep there in that picture. Next slide. Okay, this is one with no area of interest. That is the beltline weld there. Remember I told you the welds are buffed up and they look dark? So that's the beltline weld. Next slide. Okay, I wanted to talk about this one because it says on it likely calcium. Well, it wouldn't be calcium. And somebody asked a question about this because they recognize that calcium is not something that you'd find on a canister. This would be dirt, mud, dust that was accumulated here and piled up to, it's 1/8 of an inch deep. See, it's 126,000. That's 1/8 of an inch tall pile of mud there. And that happened during rain when we had water intrusion, caused mud to accumulate there. And because it was accumulated by water, it looked a little bit like the inspector who wrote this, looked a little bit like calcium that you might find underneath a faucet outdoors where the faucet's dripped for 20 years. Well, we haven't had water dripping for 20 years. In fact, our water events have lasted for hours. This would be mud. Next slide. Okay, this is a link to where our canisters are. You can see this. Next slide. And now we're going through the pictures. There's like 81 of these that we're going to go through. So this is the top of DSC 003, I think. Yeah, DSC 003. So this picture's on top. It's one we showed earlier. It shows the kind of the windrow of the dust there. I think it's a cool picture. Next slide. Okay, this one's confusing because it's upside down, okay? At the top of the picture is the rail that this canister sits on. Remember, this is a horizontal canister. And then the scratches that you see above it or below it are actually above it. Those scratches are caused by the transfer cask. So remember, the canister goes in a transfer cask, gets driven over and inserted into the storage location. The rails on the transfer cask are a different position than the rails in the storage location. So those scratches up higher there are the rails in the transfer cask. Next slide. This is a close-up of one of those scratches. Next slide. And these are another picture of the scratches on DSC 003. Next slide. I'm going fast, but all of these are online. You can take a look at them at your leisure. This is dust. Now, and notice it says it's about 1/16 of an inch thick. It's piled up there. But see, there's fibers in it. So what would cause fibers? Remember, I said everything on top of these canisters has to float in the air. So what floats in the air? It looks like this. Dandelion blooms, some grass seeds. So little, very light things that can float on the air and get blown up because they have to go a tortuous path. They go in, up, around to get on top of the canister. So this has got some grass seeds in it. It's dry as a bone. Notice the grass hasn't sprouted. Next slide. Another scratch. This is a close-up. Doesn't it look ugly? It's 21 thousandths deep. Next slide. Another windrow of our talcum powder dust piled up on top of the canister. Next slide. This is some more fibrous material. We've just labeled it dust debris. It's once again probably dandelion blooms or something similar. Next slide. Another scratch that's close up in its worst condition. Like I said, we didn't take very many pictures with nothing in them, but when we took a lot of pictures of the interesting things. So, next slide. Okay, this one's right side up. So the rail is below. This is the way it would be in real life. So the rail's below, the scratch is above. That's looking, horizontally down the canister. Next slide. Okay, this is a picture of the scratch going across the beltline weld. Remember that in the TN system, these scratches are designed in. They move on rails. It's expected to scratch exactly like this. Next slide. Now that's a close-up of the previous slide where the scratch went across the beltline weld. Next slide. Okay, now we're moving on to the Holtec system. This is MPC 55. This is remember I told you the shield ring rubs are very wide and shallow. When we tried to measure some of these shield ring rubs, and there's really no depth to them and no accumulation. They just are discoloration. Next slide. This is a couple of little scratches. Next slide. There's a close-up of that same scratch, and that's the camera. One of the cameras being taken, a picture of it being taken with the other camera. I told you each one has 2 cameras. I think that camera's about 1/4, 5/16 of an inch in diameter, about 8 millimeters, 6 or 8 millimeters. Next slide. There's the camera with the light on. Notice how it really makes everything kind of different when it turns the light on, but it has to have a light on to do its characterization. Next slide. Okay, this is a free iron transfer, one of these North American maps. This is this 72? No, this is 55. They tend to look a lot alike. They're probably made by the same patch of epoxy that was missing in the canister or in the cask. Next slide. More free iron transfer. This was also on 55. Next slide. Okay, that's a seismic support. I think I told you guys that most of the scratches were made by seismic supports. There's 6 of those. The steel that is made of is 1 inch thick, just for scale. So that's 1 inch across that piece of steel. They fit very tight because they're designed to support the canister in a very large earthquake. The light at the top is sunlight. So this picture is taken looking up. Next slide. Once again, looking up, that's a scratch below the seismic restraint. That seismic restraint right there just made that scratch. Next slide. So this is a double. So up in the top left corner, you can see there's some scrub from the shield ring, and then down below, you can see the free iron transfer. And at the very bottom, that kind of an arced, shiny thing, that's the ring that the canister sets on. It sets in a support ring. Next slide. More free iron transfer. Next slide. Close up of that free iron transfer. Water intrusion. So that's a seismic support there at the bottom left. So you can see that seismic support is vertical. So that's where vertical is in this. And of course, water intrusion always runs down. So if you got water intrusion, you can always tell which way down is because the water intrusion runs down. So that water ran down a little ways on the side of the canister, brought some dust with it, and then dried up, and it's been dry as King Tut's tomb ever since. And it'll continue to be that way. Next slide. Okay, this is a scratch. Next slide. Okay, there's water intrusion and a seismic support. Nice picture, actually. It'd be better if it was rotated 90 degrees, but we didn't rotate any of these pictures. They're all exactly like they were given to us. All we did was add the watermark. Next slide. Just water intrusion. Next slide. Okay, this is characterization of a piece of free iron transfer. And whenever you see those lines and the little green dots and the circles, that's how the camera's in the measurement mode. Next slide. And there's what we measured. Now, remember we said free iron transfer. So free iron transfer is a buildup on top of the surface. So this, it set the 0 at the top and came with a 4-inch deep scratch going down. But since it's actually a buildup on top of the surface is probably down 4 thousandths, and the 0 should be down there. But that's how the camera does it. So there's probably no scratch there, just a surface buildup. Next slide. Okay, this is also in the characterization mode. Look at those colors. So I told you before, when the camera's in the characterization mode where it's doing a surface profile and measuring, it really exaggerates or even creates false colors. You'll see some nice green ones later. So Next slide, I think, you see that was 5 thousandths deep. There's the measurement of 5 thousandths deep right there. Notice it says MTD equals 450 thousandths. That's the width of the measurement. So that's almost a ½ inch wide. Next slide. Here's another characterization of a scratch. I think we'll see it's 4 thousandths deep. Next slide. There's the 4 thousandths deep. So that's the surface profile that the camera measured across that scratch. So you can look at that at your leisure. Next slide. Okay, this is free iron transfer, and it might even have a shield ring rub in the middle of it. You can see some lines there. It's a good picture. Next slide. More water intrusion next to a seismic support. Next slide. Another seismic support with a water intrusion running down it, all dry as a bone. Next slide. Okay, here's a scratch. It's 1/1000th of an inch deep. That's even hard to measure because there's more than 1/1000th of an inch variation on the surface. Next slide. Okay, here's some nice water intrusion. That's a seismic support at the bottom. So vertical is this way, right, up to your right. I think we got quite a few pictures of this water intrusion. Next slide. Yeah, so there's a picture of it. This is some of our most dramatic water intrusion. It came in during obviously a blowing rain, washed some dust down the side and dried right up. Next slide. Same water intrusion. Goes down the canister. Next slide. This is free iron transfer. It's got a little bit of rust color to it, but it's on the surface. It's not the canister rusting. It's iron that's been transferred onto the surface from somewhere else. Next slide. This is a free iron transfer. Once again, next slide. Same one. Next slide. Water intrusion. So that's a dramatic one too. That's a nice looking picture. That's a seismic support over on the right. Next slide. Okay, this is a long rub from a shield ring, and because it's a little bit orange, probably we wiped off most of the zinc paint and we got a little bit of iron transfer from the shield ring. Next slide. This is a fabrication mark. So they had something there, they buffed it out and it left that part shiny and the rest of it's got that sandpapery texture. And of course there's also a little number there that they wrote on it. Next slide. This is a rub from the shield ring. You know, that the rub's going up and down, so that helps you figure out which way vertical is. And you're looking down into the bottom of the canister, and you can see the ring going around. That's the ring that it sets on. Next slide. Once again, we're looking down into the bottom. You can see the ring that the canister sets on, and you got a rub from the shield ring coming up the side there. Next slide. Now we're looking at the lower seismic support area, and that's a rub from the shield ring. And then a fabrication mark. See the writing down there at the bottom? That's a fabrication mark. Next slide. You know what? I was wrong. Go back to that slide, please. Is that the bottom of the shield ring, Randall? Is that what I'm looking at? Oh, that's the pedestal. Okay, I was right. So that's the pedestal that the canister sets on. That's at the bottom of the canister. Next slide. That's one of those RT marks. They've got them all over the canisters. Next slide. This is some free iron transfer on the side of the canister. We're on MPC 55 now, 65. Next slide. Or I think it's the same one, just a closer up image of the same. Next slide. Some water intrusion. It's typical of our water intrusion. It runs down the side and dries up and stops. You know, if our canisters weren't warm, they would all just be vertical streaks that go all the way to the bottom and accumulate in the bottom. Next slide. This is a nice rub from the shield ring, so you can see which way vertical is. Vertical is kind of from bottom left to top right. Next slide. This is the same rub and a camera, the camera taking a picture of the other camera. Next slide. And that's a characterization. Next slide. I think that's a characterization of this scratch. Okay, so the previous slide is the characterization showing the depth of the scratch was just 11 thousandths. Next slide. There's a good close-up of a seismic support. Actually, I think it's in contact with the canister there, and there's a little scratch on top of it, or actually below it. We're looking up there, I think. Next slide. This is a rub from the shield ring, and those horizontal lines look to me like chatter as it went down. It kind of went thunk, 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 and that's the white stuff is probably the zinc paint as it accumulated and chattered there. Next image. Say that's a close-up of the chatter area where the chatter is. Next slide. Okay, this is a characterization of a scratch. There's nothing green in there, but I told you that when we're in the surface profile mode, the colors get exaggerated or even fictitious colors get added. So we got some blues and some greens in there. The camera's in the super high resolution mode, and you know it did that. Doesn't hurt anything, and the numbers are still good. It's 8 thousandths deep scratch. Next slide.
Hey, Jerry,
Yes.
if I may, Manuel here. So we're a little behind on time, and I think maybe folks get the picture. I would just ask maybe the panel, want to make sure that we have time to address questions from the public. Have we seen enough, or we'd like to,
No, I think, Victor, did you have a question?
I was going to say, I'm glad that
I'm glad
all
we-
17.
I was gonna say-
I don't have to go through all 1,700.
Thank you for not going through 1,749.
We
Jim
only
has a
had
quick
80,
question.
we only had 81 on this list.
Yeah.
But
Okay,
that's fine.
Jim.
Well, we appreciate it. I was expecting to see your family vacation coming up here pretty quick. But so the canisters are like 7 years old. And eventually, the understanding they're 100+ years with age management that they can last. So you mentioned, I think it was like 65 thousandths was the max depth for a scratch. Sooner or later, they're going to start, these things are going to start to age and maybe age out. So I'm assuming you already have parameters in mind so that before a canister fails, that it's going to be replaced if whatever X, Y, and Z happen, that you have to, that maybe the scratch gets deeper and deeper, or the buildup or calcium or the water intrusion, whatever, something's going to trigger, okay, this one has to be replaced before it fails. So I'm assuming those parameters are set, that you have an idea, is like, okay, when these things happen, we know we have to replace this.
Well, first I want to say that everything we've seen here is static. Okay, these scratches were all installed at installation. We're not going to move them again until it's time to take them out. So there's going to be no more scratches.
Okay.
The water intrusion's been stopped by adding the outlet vent covers. We're going to keep inspecting, but as long as nothing changes, it's never going to change. We don't. I would expect that 100 years from now, it'll look exactly the same with a little dust. As long as you can keep the deliquescence from occurring, so that you never have a wet surface, nothing's going to change.
So I think that's kind of pie in the sky thinking. To be honest with you, and I know you're much smarter than I am on this thing, but there's going to come a time where they have to be replaced. And I just want to make sure those parameters are, you have an idea that, okay, maybe in 150 years or something like that, that if a certain scratch gets to a certain depth or starts to expand or things like that, and I know you're looking at it, but sooner or later they're going to have to be replaced for some reason, I would assume.
We designed them very, very well.
I believe you. I appreciate that, but nothing lasts forever.
Yeah. So,
I
when
can-
it comes time to replace them, the technology exists to replace them. It would require some equipment to be fabricated and hit. Of course, we would use the technology available at the time. It would probably look nothing like what's available now. 100 years from now, this is all going to look different. So,
Okay.
there's no need to plan for that now when you'll have 100 years before you think about it. And to invest in technology or invest in analysis now when it's all going to be different would not be useful.
But sooner or later, you're going to have to make a decision to replace a canister. So I guess I'm asking, what would those parameters be?
Oh, the parameter would be there. It doesn't meet the ASME code.
Fred,
Yep.
did you want to chime in there?
Okay.
Looks like Dr.
Yeah.
Burns.
Oh, Dr. Burns.
Raised his hand.
Yeah, I
Appreciate it.
Dr. Burns, did you want to add something?
Yeah, I was just gonna, add something. I would agree, and I would potentially disagree that it's pie in the sky, that everything is fine. I think that that's a very real possibility. I think it's part of the reason that we set up the aging management approaches is you do modeling with your best science, right? To be able to set up your inspection intervals. And then the entire concept of an aging management program, is to allow for conservatism, and you just continue to inspect. And so I think the fact that there will be a window of time to where it's cool enough to deliquesce, but warm enough to maybe crack, and we inspect through that time. Then once you get past that, this damage mode, it's not, it's not something that it is a foregone conclusion that it has to happen. And this is going to be the relevant damage mode. So I think we have a good, and this is typical with other industries, right? You have something that could potentially happen, you inspect for it, and then it doesn't mean it's going to happen. It just means that, you have a safety plan that is in place. And then one other thing that I would suggest is just details of the ASME code. All of the things that you are discussing and asking, that it's in a lot of detail in the ASM code of, what's allowable, what's not allowable, how you then adjust your inspection protocols and those sorts of things. So I think that those have been thought through, are defined, and are consistent with just the way that aging management approaches are set up throughout a whole bunch of different industries.
And I want to add that we're open-minded. Of course, we're looking. If there's something, we will find it and we'll be prepared to address it.
Okay,
Yeah.
but to me, age management means eventually it's going to age out. And so I guess I was just looking for whatever those parameters. And I guess you say if it doesn't pass the ASME standards, then we got to get rid of it. I just want to make sure whatever those are that, we're far enough ahead of any potential before the canister itself fails. So it's replaced before that happens. Okay.
Thank you, Jim. Victor had something?
I would just say, and the inspection process that you've talked about will ensure, I would think, that we become aware of any problem long before it's a serious problem.
Exactly. Well, that's what we are inspecting, and we are open-minded, and we are looking for anything, and we're prepared if we find something that needs to be investigated, to go back in and do more investigation. There's more equipment available to do deep, we see something, there's equipment to do volumetric examinations, for example. But so we're prepared. I just want to, I think I want to try to make people feel good that these canisters will last a very long time.
And prepared to repair if need be. So
I'm sorry, Fred, into the
Yeah.
microphone, please.
I was just adding that we are also prepared to repair if needs be. And if there's a need for a repair, we have the technology. We know what we're looking for. We know which area are potentially someday prone to this type of corrosion. And that's where the aging management plan comes in. So we'll continue to monitor. Whenever we see anything, we'll address it.
Jim, I remember back in the early days, before this actually took place, Dr. Singh was here, and the question was asked of him, what would we do if there was a leak? And that was before the repair system came into being. And he said, well, we would actually put them into another canister. and kind of like a Russian doll. But now we've got the repair systems, so should something come up long before that, they could repair that. So I'm looking to see if there's any other questions. John,
just a quick question for a frame of reference. When you're talking thousandths of an inch, what's the thickness of a credit card? Let's say, how many thousandths would that be? Just so that I can wrap
Isn't
my
a
mind.
credit card about 30 thousandths? I think so. A sheet of paper, of copy paper is 4 thousandths.
Okay, just so I understand, when you say a scratch is, 10 thousandths, I don't know what that is.
Right, so 12 thousandths of an inch, which is a lot of scratches. We saw around 12. That's 3 sheets of copy paper.
Okay, thank you.
Okay. Looking around, I don't see any other questions from anyone here, so I think we're going to go ahead and move on to the next slide, please. Once again, thank you, Dr. Burns. Let's see. Okay, here again are the directions for public comment. The CEP comment form link is available to submit a question or sign up to speak online. For members of the public joining us in person, please remember to complete a CEP question comment card available at the entrance, and we will add your question to the list in the order they are received. If you wish to speak, fill out the same card and we'll add you to the queue for public comment. The names of individuals who signed up to speak will be displayed on the slide, and I will call your name when it is your turn to speak. 3 minutes, please remember that. Countdown timer, as always, will be on the screen. We have a full hour dedicated to public comment segment of the meeting. And after the public comments, Victor is going to facilitate public dialogue and addressing any questions in the order that they are received. And with that, I don't see any other questions. We're going to take a very quick 10-minute break.
I don't think Manuel's coming back up.
Okay.
Manuel's not coming back up.
Okay, we're going to go ahead and start then. Once again, thank you for those that are going to be speaking right now. So first up in the speaker queue, we have Alice McNally, and then we have Gary Hedrick on deck. So Alice, are you here?
I'm here. Can you hear me?
Yes.
Okay, I guess you're calling in.
No, I'm here. Can you see me? I'm here. Hello?
You're online. Okay, we can hear you. We can see you too. You're ready.
All right, thank you. First, I did want to say that the casts, the 5/8" casts, or canisters at San Onofre are only warranted for 20 years. They're temporary. All right, here we go. The SCE must agree that it is time to work together to move the waste to higher ground. At San Onofre's current nuclear waste storage system puts all of Southern California at risk. 8 million people living and working within a 50-mile radius are at risk. San Onofre has become a de facto nuclear waste dump site for the foreseeable future. Spent nuclear fuel is the most toxic material known to man and remains active for hundreds of thousands of years. Tritium is in the groundwater and leaking into the sea. Dr. David Richardson, professor of environmental and occupational health at UC Irvine, warns of the potential health risks even if a fraction of the material were released. An accidental release would double the leukemia risks for young children living within a 50-mile radius. 1,800 tons plus are stored in temporary, thin-walled, non-transportable canisters. Song's waste is stored in the most dangerous location in the nation, only 108 feet from the surf, behind crumbling and cracking infrastructure. Consolidated interim storage may not become a reality. The courts have said no to Texas, and New Mexico will not accept our waste. Surfrider Foundation warns that 70% of Californians' sandy beach will be lost by 2100. How can you continue to ignore the reality of climate change, rising sea level, more severe storms, water sprouts, and tsunami warnings, conditions that have been continually denied and ignored or called unrealistic and unlikely by the CEP because you want to keep your jobs? Trump's executive order lessens regulations and cuts corners to rush the licensing period, plus the scratches, gouges on the canisters from handling, no emergency plan outside the plant, no necessary equipment at the ready, such as a crane or a hot cell, bring up serious questions of public trust. You can't possibly compare the safety of our 5/8-inch walled cans, which are guaranteed for 20 years, to the 10 to 12-inch thick-walled European casks and their methods of storage. Stop the lies and denials. You can't possibly believe this stuff. It's time to get real and work together and move the waste to higher ground now. 2040 will be too late. Thank you.
Thank you very much, Alice. Gary Hedrick, would you like to stand up to the microphone, please?
Yes, thank you. And there are a lot of concerns besides what we're covering tonight, and I'm not diminishing those or anything, but I do want to say what a great relief it was to see canister number 72 5 years ago and 5 years now, and to not see a big difference. And I tell you, that was a very stressful thing for the public to not be able to see the photos. And so I will continue from there. I want to express my appreciation to Southern California Edison and to everyone involved for taking this genuine step forward. Your decision to release all of the inspection photos is a meaningful gesture of transparency when you had previously considered them to be company confidential. This is what trust looks like. It's not just about showing pictures, it's about showing good faith. When the public and the experts can look at the same facts together without filters or secrecy, that's when real safety begins. We're not here to assign blame or prove anyone wrong. We're here to make sure no important assumption is left unchecked, because when it comes to nuclear waste, the stakes are simply too high. This is about protecting our families, our coastline, and future generations. With Edison's new transparency and with the City of Irvine helping to guide a collaborative Plan B process, I feel confident that capable people will be able to work together in good faith toward a permanent solution. I also see this as an opportunity for me to step back and focus on other things that I've needed my attention, taken my attention away for far too long. I'll remain available from time to time to share local perspectives, but I believe this effort is on a much better path now, one guided by a team of experts that the Mayor of Irvine is in the process of bringing together. Let's keep building on this moment with transparency, respect, and honest science. No secrets, no spin, just the facts on the table, so we can all be sure nothing important is being overlooked. The nuclear waste challenge is bigger than any one city, company, or agency. It's a national responsibility, and together we must do whatever it takes to make sure we get it right. Thank you.
Thank you, Gary. And Gary, I understand you said you're going to be stepping back a little bit now, but whatever, I think I want to speak on behalf of everyone for all of your activities, your voice, for many years in addressing this important issue. I think everyone owes you a great deal of thanks and gratitude. So with that, we're going to move on. Next, we have Nina Barbier. I'm sorry. Yeah.
To Gary, we still need your help with that Plan A, getting it out of California, because I think that's our number one objective here in California and for this city, is to move that somewhere else, or internationally or outside of California, and that's our number one objective, and we'll continue to work on that, and we need your help on that.
Thank you, Victor. Thank you, Gary. And so, Nina, are you calling in? Have we got you? I know this is always a challenge. Oh, we see you. Okay. But it looks like your microphone is muted.
Can you hear me now?
We certainly can.
Dan, before my time starts, I just want to let you know that I sent you three emails, and so is Charles. I was on hold on the phone for about 32 minutes. I've called in 3 times. I got in, it indicated that I could join the meeting, and then there was nothing but music. The second call, there was nothing but silence, and the third call, there was nothing. So I have no idea who else was trying to get in, but I came back to the office to get in on the website. So I just wanted to let you know that. And something to consider, all the meetings in the past as well as tonight, the chat has been disabled. And there's no way to let anybody at Edison know there's a problem. So please consider at least leaving the chat open so that we can communicate with Edison if there's a problem. Thank you. Gary, thanks so much. I asked if I could give you that information without expending my time, but it looks as though my time is being expended anyway. On the afternoon of September 30th, Dan Stetson presented a PowerPoint at Mayor Larry Agron's special Irvine City Council meeting that focused on the radioactive nuclear mess at San Onofre. A few of his slides focused specifically on spent fuel solutions funding. Slide 15 listed the funding sources of spent fuel solutions as Orange County, San Diego County, Riverside County, and then SDG&E in Southern California Edison. Because Dan moved on without talking about the source of those funds for action for spent nuclear fuel solutions now, public watchdogs made further inquiries about the City of Irvine meeting after the City of Irvine meeting, such as what are the funding source that the SDG&E and Edison used to contribute to spent fuel solutions? Was SDG&E and Edison's funding source the Ratepayers Decommissioning Trust Fund? If yes, how much of the Decommissioning Trust Fund was expended by Edison and SDG&E on spent fuel solutions? Dan engaged Manuel Carmego to facilitate our answers, and we found that and would like to share with the community the answer to that, and then I quote, since the creation of spent fuel solutions in March of 2021, Southern California Edison has spent a total of $896,000. And during that same time period, SDG&E has spent a total of $235,000. That said, ratepayer decommissioning trust fund dollars that the Southern California Edison and SDG&E use to fund spent fuel solutions is currently at $1,131,000. Since the source of the funds were actually the ratepayer decommissioning trust fund, I hope that the next time the funding source for spent fuel solutions is presented or discussed, the funding source for the ratepayers will be acknowledged and identified correctly. And when we're talking about transparency, whether it's county money, city funds, ratepayer decommissioning, the public is paying for everything. We have a right to know what the public and the ratepayer funds are being expended on, and expended and on what. And if we have questions regarding those funds, the public and the ratepayers are on a need-to-know basis, and we have a right to know. Thank you.
Thank you. Thank you very much. We're going to move on now to Daryl. I'm not sure if Daryl is here or if he is going to be online. So, okay, it looks like we have identified him. He's not here in person, and we don't see him online.
Daryl's a woman.
They had to leave.
Oh, had to leave. Okay, so we're going to go ahead and move on then to Stephen Sharma. Are you here or online, Stephen?
Hello, hi. Thank you very much for indulging me. I am a physicist from the University of California, Berkeley, USC, the American Physical Society, the American Nuclear Society, the National Academy of Sciences, Engineering, and Medicine. I am a proponent of nuclear fusion, and I'd like to see a San Onofre National Laboratory built with a demonstration reactor to refurbish the San Onofre Nuclear Generating Station site. CAS, the storage, the canister storage, is an issue. I think we need to take advantage of the footprint and the infrastructure that's already built, and we have to address the issue of nuclear waste with a fusion commercialization project. And taking advantage and thinking of the future, we've got to develop a paradigm with Senate Bill 86 that just passed in California, giving tax incentives for fusion energy. There are 53 fusion projects in this country and $10 billion of investment. California needs to lead the charge in nuclear fusion. A San Onofre National Laboratory, a San Onofre demo reactor, could connect to the grid and provide clean, space-efficient electricity with the PID LQR feedback revolution, the Hall effect sensor, magnetic plasma shaping, and turbulence mitigation with neoclassical turbulent transport mitigation. These are technical issues that the Division of Plasma Physics is working on. IAEA conference goers and Chengdu, China are working on. It's an international collaboration. And if there are lessons that we learn in nuclear, it's to think globally. There's 600 some reactors producing about 10 to 20% of global power. And nuclear is a viable option for carbon-free emission. And we need to refurbish the San Onofre site. I would love to see a new Camp Pendleton, like a model city built, something that can help people with a urban planning design. And in regards to the cast and the canister development, Yucca Mountain is not a viable solution, and we can store this stuff on site. I think the risks are a little bit exaggerated. There have been 3 nuclear accidents over the course of the 50 plus years of nuclear science in this country and in the world, and these accidents are rare, and there has been very few incidences of nuclear contamination. I think there's some barrels that have been released into the Pacific, but these are less than 1%, or not even 1% of the contamination. So I'd like to refurbish the site. I would love for you guys to discuss a new national laboratory built at San Onofre and a fusion power plant. Thank you.
Thank you, Stephen. We really needed you this morning at UCI. I was there. They had it's still going on. They had a full day conference on energy, everything from renewables to spent fuel. That I spoke on that, but there was also a topic on fusion, but a lot of things going on in a lot of different spaces right now. So thank you very much for your comments. I don't see any other names here in the speakers queue, so my understanding is we're ready to go ahead and turn it over to Victor for those that have submitted questions online.
Let's do that.
Let's move your microphone a little closer.
All right, let's also do that. All right. Let's start. I'm not sure how we're going to handle this. I wanted to ask Manuel, but we had a list of questions submitted by Shannon Chu, and I don't know if we were going to handle those first or at the end because there was several questions.
I can do that now.
Okay. All right.
Okay, so Shannon submitted a list of 10 questions, and the answers are technical and long, very good questions. So I'm going to answer I'm going to summarize them now. So Shannon, thank you very much for your detailed and technical questions. And I want to say we've enjoyed working with you during your time at EPRI and wish you the best in your next endeavor. Many of the questions that you asked have been addressed in our presentation tonight. But we've written out detailed answers that we will post online in the next week. And right now, I'll just give you a quick summary for everybody here. So your question about stress corrosion cracking prevention, as you know, stress corrosion cracking requires an electrolyte solution of salt, tensile stress, and a susceptible metal. We use 316L and laser peening to induce compressive stresses, and it makes SCC highly unlikely, if not impossible. So no SCC has ever been observed in the industry. For our mitigation strategy, if a through-wall crack were to occur, we've developed cold spray nickel repair equipment. We've got it staged, ready for deployment. We could do that with a 7248. Your observations of, you ask about rust observations. It's actually, as we discussed in the meeting, free iron transfer from the carbon steel cast and the canisters themselves are not corroding. That's more discussed in the detailed answer. Our inspection capabilities, we've got visual inspections that are effective in detecting early signs of stress corrosion cracking. We look for the pitting and the red-brown corrosion. Then advanced techniques like eddy current and ultrasonic testing are available should a crack be detected, but no cracks ever been detected in the industry. Your concerns about canister integrity under the free iron transfer stains, the inspections of canister 72 in 2019 and 2024 showed no change, and it was felt very good to hear Gary say that caused him to relax a little bit. So I'm really glad that he agreed with the way we interpreted that. If stress corrosion cracking were initiating under the stains, the large amount of red-brown corrosion material that would be associated with it would be quite detectable. And for the radiological release risk, even in the event of a crack, now we say that a release is not credible because our design does not consider a through-wall crack as a credible event. Okay, so there's zero release associated with a through-wall crack. But Shannon's asked us to talk about if a through-wall crack did exist, and even in the event of a crack, cobalt 60 would be very minimal because of the tight crack geometry. And we've done a lot of research on our filters used during the drying process, and no cobalt accumulate, or almost no cobalt accumulates on those. So that tells us that there wouldn't be cobalt released. And then fuel cladding safety. At the low temperature of spent fuel cladding would not degrade due to air against the cladding. So that's a summary of the detailed responses we posted soon.
All right, that sounds great. And then our last question, I already talked about SBC, clean energy, San Onofre's role in clean energy, some facility at Camp Pendleton, but more importantly, talking about referencing Senate Bill 86, spearheaded by California support for advanced manufacturing and fusion. He suggests we need a new national lab at San Onofre, the new fusion reactor called DEMO, from schematics developed by international collaboration. We can produce cheap, reliable, space-efficient, limitless electricity with the new PID, LQR, Hall effects, sensor magnetic pixelated plasma shaping, and turbulence transport mitigation. It is a green revolution. The Army, the Navy, the Air Force all want SMRs for their bases and ships, new fusion technology, and better power production. Why is there so much traction and friction for a fusion plant? What is the psychology of the contrarian nature directed to this anti-progressive movement, suggesting there's a real need for energy in this country, given the demands of AI?
So Ron, I don't think Ron's here. Want me to take that one? So that was Stephen Sharma, who we just heard from on the last call. It's great to hear his enthusiasm for new technology and new energy, but San Onofre's on leased land from the U.S. Navy. The Navy has indicated they want the property returned after demolition of songs, and so it's up to them. It's not up to us.
Right.
Yeah. Also, I'd like to add, I mentioned that Manuel and I were actually at a conference earlier this morning, and one of the presenters spoke specifically on fusion. And I was quite honestly surprised at the number of companies and the investments that are now taking place actually in California, a lot of it in San Diego on fusion. So, I mean, it gave the impression that it's going to happen, it's down the road, but there's a lot of energy and right now, a lot of venture capital being poured into that. So it's something that I think we are all going to keep our eyes on, because I think it's going to be here, I don't know when, but it's coming.
Yep.
All right. There was a question written, submitted about moving the waste to higher ground now, that there's no time to waste. The SCE must agree that it's time to work together to move the waste to higher ground. San Onofre's current nuclear waste storage system puts all of Southern California at risk. 8 million people living, I guess, in the proximity to that. So I think.
I can take that.
Okay, all right.
I'd like to say that, as I mentioned in the introduction, we agreed that the spent fuel was never intended to stay here, to stay on site. Having said that, I think we should partner to work and clear San Onofre of spent nuclear fuel. It is safely stored now. It will not be any safer if it's relocated elsewhere on Camp Pendleton or in bolted lit casks. So I think we need to come together and work on solving the spent fuel challenge for the whole country. There's a window of opportunity opening to do just that. So anyone who wants to help and join the Spent Fuel Solution Coalition is a very effective way of doing so.
All right. Next question is from Gary Hedrick. It's submitted in writing. Please ask Dr. James Burns to give his opinion on how long these canisters can be relied on under these conditions without any intervention taking place. Some say 20 years, some say 40 years, and I've heard 100 years or indefinitely. What is the best guess if we are going to play it safe? Will there be more frequent inspections of canisters as suggested by other experts in the field? And will Southern California Edison consider re-inspecting canisters with known areas of concerns, or will they limit inspections only to the oldest and coldest canisters? And I think we'll, well, he asked that of
Dr. Burns.
Dr. Burns, yeah, and also.
I can talk to it if Dr. Burns isn't available, or if he wants me to address.
Oh, he's on.
There it is.
All right.
Yeah, Jerry, you can talk to it if once you're done. If you want me to augment, I can chat as well.
Okay. So interestingly about the frequency of inspections, the NRC has made some presentations recently at industry meetings, say that they're looking at inspection frequency, and based on the data of inspections that are being performed, they're looking at actually decreasing the frequency, increasing the interval between inspections at some of the inland plants. Now, the inland plants are less susceptible. No word yet on the coastal plants, but we anticipate that the frequency of inspections will probably stay the same. As far as which canisters to inspect, we will follow the guidance of EPRI technical report on aging management, which tells you how to select the oldest and coldest. That's endorsed by the NRC, and it's a requirement of our license. And it requires, so the way that works is we inspect one canister as a repeat, and one canister, a new canister each time. That's every 5 years. We select the new canister out of the oldest and the coldest population. As with respect to canister 19 is one of the new homes canisters. It's been a topic of discussion because there was an AR written on it when it was installed. There was the scratching was deeper on it. We did some analysis then, and we concluded that the scratches were 10 to 15 thousandths deep. And the question is, are we going to go inspect it? We haven't chosen the future canisters to inspect, but canister 19 isn't in the oldest and coldest population that would be required by the guidance that tells us how to pick our canisters. We did, do some detailed analysis at that time. The metal shavings that came off were retrieved. They were sent to a very good laboratory who did some analysis on them and helped us understand that the depth of the scratches were 10 to 15 thousandths deep.
All right. Gary also had a follow-up question about canister number 72 in particular. From slide 51, is a gouge in the photo on the left the same area as a measurement on the right? Because it looks like it's on a curve and not longitudinal.
Yeah, so those photos on slide 51 are the same scratch, but when you're looking at the scratch through different lenses at different focal lengths from a different angle, and remember I said that things look different when you're in the characterization mode where it's measuring the depth. So those pictures do look differently, and that's something that I that I was explaining. Had to hurry a little bit there on time, but that was one of the points that I really wanted to make. When you're characterizing a scratch, that the picture is going to look a little different. Okay. The second question about likely calcium. So I explained in the presentation that that wasn't calcium, but that was dirt and dust.
All right.
Okay.
One other question from Gary. Why aren't there more photos of the welded areas, since that's the most likely area to see problems first?
Okay, so in 2019, remember, we went in there to inspect the scratches. That's what we were asked to do. We weren't doing an aging management inspection of the welds. In 2024, we did do an aging management inspection of all the welds, but we only took pictures of something of interest. So I think that's a very good point, and I think we should have more pictures of the welds, and in future inspections, I'm going to ask for more pictures of the welds, even if, to document that the welds are fine. Thank you.
Thank you. From Ellis McNally, there's a mathematical error in the percentage of dose exposures from the liquid batch release alert for the March 2025 alert. This has been verified by 2 mathematicians. Is there a one-time error, or has this been continuous? And Ron's not
here, and this is an issue I'm not familiar with. I can read an answer that Ron wrote. He said, thanks for the note and pointing out the typo. The annual whole body dose limit of 0.004098% is not correct. It should be 2098%, 0.009. This will be corrected on the website. The percent of whole body dose for the March release was 0.008 and some more digits, as you have calculated. However, this is only for the March release and cannot be directly compared to the percent of annual whole body dose limit, which is a summation of all of the dose for the year. We had discussed the calculation method in the third quarter 2024 CEP meeting, slide 47, and there's a link to the meeting in the slide deck here.
All right. We had a question from Nina over the phone. She pointed out, and we'll have to correct it, that there was several issues with access on the phone. We'll address that outside of this meeting. But she also had a question about for Dan or others about your slides at the Irvine meeting, at the listening session, I guess, at the Irvine City Council Coalition, the funds and how much is being spent, $896,000. I think that's us, STG&E spent 235, 1 million plus altogether. Do you have any update on that, or you can get back to that, or?
Dan,
well, let's see. With reference to that, what we're addressing here is the amount of funds that the Spent Fuel Solutions, what it cost. And I do know, thank you very much for the County of San Diego. You guys have been pitching in $100,000 a year, as has the County of Orange, this same amount. And the other amounts, I think, I'm not quite sure what the totals are. I know that those 2 numbers are accurate. Fred might have a little bit more input in terms of what the other numbers are. Manuel, we did respond to Nina with some of the numbers, but maybe you could add a little bit more light to that.
Yeah, Manuel was going to take that one. Here he comes.
Can you hear me?
Yes. Yeah.
Okay. Yeah. Sorry about that. Yeah. So appreciate the question from Nina. The source of the funds is to. I'm sorry, I'm getting my own echo here in the room. The source of the funds is to run our coalition, and it's of course important to do that in a professional manner. And so we have an agency that supports that work, as Supervisor Desmond mentioned earlier. I would highlight that there's a process called the Nuclear Decommissioning Triennial Proceeding that we do at the California Public Utilities Commission that looks at the prudency of our expenditures. And we just went through that process for in 2024. And I would just highlight that there were no challenges from the California Public Utilities Commission or from interveners who are paid to participate in that critical review process. But I do appreciate the comment about the source of the funds, and we do use trust funds that were contributed to by customers over time in order to fund the work of the coalition.
Yeah, I think those are really important questions, really, not only about the source of these funds, but, periodically we review the funding and how things are going with relationship to the budget. We know that there's a certain amount of money that has been collected, so it's always good to know how we're doing, if we're staying on budget, and if we're going to have enough money to complete the full decommissioning, which I think, Fred, you do, right?
Oh yes, we do, and I appreciate the comment and feedback, and being transparent in this area is pretty important too. I think we should make this available. Maybe we can post a more detailed answer to this question also.
Okay, I think that'd be great. Victor?
All right, yeah. Another comment from Daryl. I think he's the gentleman that had to leave to catch the train, but he did leave his suggestion in the back, and he says the nuclear waste needs to move as soon as possible. And I think that's a suggestion, but it's something that I think we all concur with as a committee. That's our #1 priority beyond safety, is moving the nuclear fuel as quickly as possible. If someone else wants to comment on that?
That's good.
I think we're all in agreement there.
All right. And then I think Charles Langley, Executive Director of Public Watchdogs. Thanks to Gary Hedrick, San Clemente Green, Dan Stetson of the Ocean Institute, and Fred Bailey of Edison for fulfilling the spirit of community engagement by working to disclose the photos of the damaged canisters, including the instances of what appears to be corrosion. Sunlight is the best disinfection, and Edison's new willingness to share photos, the scratches, gouges, and rub marks of the canisters, a great step in the direction of honesty, clarity, public transparency in the administration of nuclear waste and the public's money and the ratepayer-funded decommissioning trust fund. Again, that's another issue I think we all agree with. I think us as elected officials that sit as representatives, elected representatives of our communities, our #1 objective is public safety. I think we all agree, and so we sit independent of this board, acting independently to make sure that this board does whatever it takes to be transparent with the community, because it affects us all. I don't think there's any other questions left.
Okay.
I think the question I asked for Dr. Brown got overlooked. If he could answer the time period he would estimate for if we had a canister that was not mitigated in some way, how long would he estimate? 20, 40, 100 years, based on his knowledge?
Yeah, we did ask him. I don't know. I'll repeat it for him if he's still here.
No, yeah, I'm here. I'm sorry. Just getting my camera and everything back up. Yeah, Gary, thank you for the question. I think you worded it very well, right? How long can these canisters be relied under these conditions without any intervention? And I think the answer is almost in the question. As of right now, my opinion is that with the current aging plan, aging management plan is a good current aging management plan. And so with the inspections that are being done and the ability to be responsive to those inspections, I think that they can be continued to operate in that paradigm indefinitely. And I guess I would reiterate a comment I had before. I don't think that CISCC is necessarily a foregone conclusion that it is going to happen at some given time, right? I think it is a possibility, and in my opinion, an unlikely possibility, but I think it is being prudently handled by the aging management program to where you're going to find it before you have any problem and have plenty of time to be able to address any issues that you have. And so, just responding to the very nicely worded question you had of how long can the canisters be relied on under the current conditions, I think indefinitely, indefinitely, because they're being inspected and I think managed, and there's a responsive management program.
All right. I think we've gone through the question.
So I hate to make the meeting any longer, but we didn't address Shannon Chu's second set of questions that she submitted today.
I'm sorry, go ahead.
There's the second set of questions from Shannon Chu that she submitted today.
Oh, okay.
I'm sure she's online waiting for an answer.
Okay, well, let me, I thought they were the same question, so it's my mistake. So, okay. I guess slide 8, canister breach.
Yes,
by,
that's it.
CISCC is a credible event. That is why SCE inspects for CISCC. Has any analysis been conducted to determine if a release will occur if the canister has already been breached by CISCC prior to an accident event? And then related to slide 39, indicates that canister surface temperature will stay above 45 centigrade until after 50 years in storage. Canister's thermal models are known to be inaccurate. Measured surface temperatures from a system similar to MPC 72 just after 10 years in storage range from 21 centigrade to 48 centigrade. Reference dry storage system inspection, visual thermal and radiation dose measurements. Can canister surface temperature measurements, canister surface temperature measurements should be collected and reported for MPC 72. And then relative to slide 48 and 49, there's a free iron transfer on MPC 72. NRC's MAPS reports on page 455 states as follow all of the shops and handling procedures. And that's, I don't have the complete question, but you might have it.
Yeah, and that's pretty much it. So I'll answer the three parts of the question. So the first part, CISCC is recognized as the most likely degradation mechanism for dry cask storage, as we've talked about tonight. However, the consequences of a through-wall breach are not, of the confinement bar, is not analyzed in our SONG system because it's not considered a credible accident, okay, in our safety analysis report. So the NRC-approved aging management program is intended to detect and mitigate degradation before it results in a through-wall breach. Thus, release through a through-wall breach is not a credible accident, and therefore there's no credible accident that results in an off-site release. With respect to canister temperature, I'm going to say something here I've never said before. So we realize that canisters will eventually cool below a deliquescence threshold temperature. So we've been working for years on a strategy to control airflow through the storage unit to ensure that the temperature stays above the theoretical limit for the onset of deliquescence. That's a very conservative, high number, and we keep the temperature up there. We'll basically make the canisters stress corrosion cracking proof. So for the Holtec system, the chain has been designed, engineered, and approved by Holtec, and it's with the NRC right now for review. So we can't get ahead of the NRC, but once the NRC is through with their review, we'll be making an announcement possibly within the next year, okay? And of course, within the next year, that means the canisters are still less than 10 years old. So okay. That's very early in their life. On the TN system, the work is in progress to do the same thing over there, although those canisters are very dry and they're further from the ocean and not nearly as exposed to a harsh environment.
Dan, I think that exhausts the questions and answers, and we'll turn it back over to you.
Thank you very much, Victor. Great job tonight, by the way. We miss Martha, but you did a commendable job. Okay, so let's go on to the next slide, please. And Fred, I think we're going to turn it over to you for some closing comments.
Okay, thank you. And I want to begin by thanking our panel members and the public for your thoughtful participation in tonight's seminar. Special thanks to you, Dr. Burns, for joining us and providing a valuable insight into chloride-induced stress corrosion cracking. It was very helpful and essential to have you here tonight. Let me also remind everyone of our guiding principles. Those are safety, stewardship, and engagement. And making the 1700 plus inspection images publicly available is a reflection of our commitment to engagement. And my personal commitment to safe storage of spent fuel on site aligns fully with our principle of safety. And we'll continue to keep the CEP and the local communities informed as we move forward with both decommissioning our plant and also the future canister inspections. Now, let's be clear again, the spent nuclear fuel stored at San Onofre was never intended to remain on site. I think we all agree on that. We share a common goal, and to find a path for removing these canisters from the site as soon as possible. Not because they are unsafe. Let me repeat that, not because they are unsafe. The fuel's being stored safely, but it was never meant to stay here. It's the federal government's responsibility to take possession. And from our standpoint, we're not in the business of storing spent nuclear fuel. As we work toward that shared goal of removing the fuel from Southern California, it's important to recognize that misleading claims about safety risks or hypothetical catastrophes do more than misinform. They undermine progress. Such claims make it harder to identify and engage with potential host communities for consolidated interim storage, disposal, or recycling solutions. Not just for our fuel, but for others across the country. So let's stay focused on the facts, on safety, and on working together towards a responsible and permanent solution. Thank you. And as always, if you haven't seen our spent fuel storage, come and visit the site, lay your eyes on the storage system. You're welcome. The members of the public are welcome, and we do public tours. Thank you.
Thank you, Fred. I think next slide, if we could, please. We want to mention that there's quite a number of resources which are available. You can go online to songscommunity.com and check these out. And now if we could move over to the next slide, please. Real quickly, I really want to thank everyone for participating in tonight's meeting. I also, as I look around the room in the background, I think I counted over 20 computers. So there's a very large technical team that is back there. I know you're trying to make me look good, but whatever you're doing, I really appreciate it for everything that you've done throughout the evening in terms of making this program available to as many people as possible. In terms of key takeaways for me, I think number one key takeaway is SEE's commitment to transparency and how important that is in really to build trust within the community. So that's number one. Number two, I want to thank Dr. James Burns as he talked about the canisters and that they didn't show any real signs of corrosion or potential problems at this point in time, and that they can be stored there very safely for a very long period of time. Of course, we don't want that, but we want to move them out as quickly as possible, but at least right now, they're stored as safely as possible as they could be. There's a repair method, number three, so that should something come up, there's a repair method that could be employed. And number four, we want to thank Jim Desmond and Katrina Foley for their continued efforts in spent fuel solutions and going back to Washington and raising the flag that we really need the federal government to get things in gear and to get that spent fuel out of here. And with that, let's move on to the next slide. Here you can see our upcoming schedule. Our next CEP meeting will be November 13th, and that'll be online. So I welcome everyone to come to that. The next topic is going to be expression of interest. It's going to be continuing on consolidated storage. The expression of interest that really relates to consent-based siting. We were hoping that we could tackle that subject, but it looks like things are moving a little bit slower than we expected, so that'll probably get pushed into next year. And then finally, we have our rescheduled our CEP member consultation meeting. That's just for the CEP members to Monday, December 15th. And this one's not going to be in person. This is going to be via Microsoft Teams. And invitations have already been sent out. And with that, let's move on to the next slide. And unless there's anyone else, I think we all want to say thank you for participating, and we'll see you next time. Thank you.
Thank you.
Dan.
Thank you, Dan.
Woo, woo, woo.